Characteristics of quasars. When quasars were discovered, we knew they were far away, and we knew they looked like stars. But in order to figure out what is a quasar, we needed to know more about their characteristics. So the fact that they are very far away means that we are looking very far back in time. So far back that we are looking at the early universe. So we are seeing things that occurred when our universe was young, when our universe first formed. So whatever these things are, they're telling us something about the beginning of the universe. These things have to be incredibly bright for us to even see them. So we're looking much farther than we're looking to see, say, these two galaxies that are in this picture. And yet it's comparable in brightness to those two galaxies, but 10 to 100 times farther away. So it's got to be brighter than the brightest galaxies. We've never seen something this bright before. When we study quasars at different wavelengths, we find that they give off X-rays, ultraviolet, visible light, radio waves. So here we've got, this is an X-ray image, I'm pretty sure, and ultraviolet and radio. Now, of course, that previous image where it looked like a dot, looked like a star, is a visible light image. So they're giving off all sorts of energy, especially if you're giving off X-rays. We know that's high energy. And yet it's also giving off radio waves, which is low energy. So what's up with that? They change in brightness. So if you're watching a quasar and measuring brightness versus time, you might see it get brighter, go back to normal. Maybe a little while later, it gets brighter, goes back to normal. So it's not something that's constant. It has something happening that makes it suddenly get brighter. Well, it turns out when things change in brightness, we can actually use this to figure out the size, as strange as that may seem. And in general, the time to vary in brightness gives us the maximum size. So if it was brighter for, say, 2 days of brightness, then that means it is at most 2 light days across. So instead of measuring it in light years, because it's such a short period of time here, we would measure that in light days. If it gets brighter for 7 days, it's at most 7 light days across. So let's look at a couple examples of what's actually happening here. So let's look at that last one, the 7 light days example. So let's say here's something that is 7 light days across. And let's say it gets bright for 1 second. And so here we are on Earth. So first we're going to get the light from the near side. So in terms of brightness versus time, we do this in days, so day 1, 2, 3, 4, 5, 6, 7, we'll do 8. So that first beam of light from the near side, we'll suddenly see it get brighter. Well, if we go in, try to divide this into 7 parts. This is going to be interesting. So 1, 2, 3, 4, 6, pretty good. So next day, we get the light that was 1 light day further in, so it had an extra day to travel before it reached us. The next day, we get the light that traveled 2 light days to get to us. Then we get the light that took an extra 3 days to get to us. And then the light that took an extra 4 days to get to us. Then the light that took an extra 5 days to get to us. And 6 days to get to us. And then finally, from the far side, light that took another 7th day to get to us. And then it's going to go back down to the brightness it was before. So we're going to see it get bright for 7 days and then go back down to the original brightness. Now if it had instead gotten brighter for 5 days, then we're going to add 5 days to the size, and that'll equal the time that we observe the brightening. So that's why this gives us a maximum, because in this case we would see it as 12 light days. So this would be a total 12 light days. And so from that we would say, well, it's at most 12 light days across. It can't be smaller than that, because if it was smaller than that, I'm sorry, it can't be larger than that, because if it was larger than that, it would take longer for the brightening, because you've got to have the light from the far side adding into what we see. So this technique gives us the maximum size. It could be smaller, but it can't be bigger than that. From this, we have found that quasars are relatively small, few light months across. That's about the size of our solar system, which, yes, I know that sounds big, but in terms of the universe, our solar system is a tiny speck. Certainly compared to galaxies, our solar system is a tiny speck. Remember, our Milky Way is about 100,000 light years across. So, imagine a couple months compared to 100,000 years. So that's small compared to galaxies. So we'll put in our little context here, small compared to galaxies. So the amount of energy coming out, all that X-ray, ultraviolet, visible light, radio waves, we're getting energy of 100 galaxies, but something the size of the solar system. So it's still really, really mysterious. What the heck are these things that we are calling a quasar?